Hello everyone. So in this lecture we will talk about word representation. Last class we finished the language model, the language modeling part of it, right? We discussed statistical language models, different types of smoothing techniques, and how to evaluate a language model, right? Perplexity we discussed in details. What is perplexity, how it is linked to entropy, and how you can use perplexity as an intrinsic measure to evaluate the performance of a language model. Okay, so now we are moving towards the semantics. Remember the different layers of NLP I mentioned: morphology, syntax, semantics, right? And so on and so forth. So here we start talking about semantics, right? The first thing in any semantic understanding of language, right, what we do is to represent a word or represent a sentence, represent a token, right? And we will discuss in this class, we will discuss old school methods to represent a word, and then we will see how modern days we represent a word using word vector. Okay, but first things first, as usual, breaking news. So on July 25th, Google DeepMind announced that their alpha proof and alpha geometry 2, which are empowered by Gemini, they have a great reasoning ability, right? They perform significantly well in International Math Olympiad questions, and they claim that out of 6 questions that are usually given to students who appear for Math Olympiad, this model solved 4 questions, right? So this is the tweet posted by Jeff Dean. He mentioned that so far any AI model was able to solve maximum 2 problems, right, out of 6 problems, but this time this model was able to solve 4 problems out of 6 problems. Each problem has 7 points. So the alpha proof model, so it got 28 marks out of the total marks, right? And this marks is equivalent to getting a silver medal in International Math Olympiad. Okay, so this basically says that this kind of models are quite efficient in solving maths reasoning problem, and these are extremely tough maths reasoning problems, right? And these kind of models like Gemini models, which is significantly large, this has this kind of capability to solve complex problems. But again, this is a significantly large model. We do not know whether a small model will be able to solve these kind of things efficiently or not. But if you want to know more about alpha geometry 2, which is the second version of alpha geometry, right, you can look at this link and you get more information about it. Okay, so let's get started. Meaning of a word, right? So let's see what a dictionary says about a meaning of a word. If you look at the Merriam-Webster dictionary, online dictionary, it says that a meaning is essentially the idea that is represented by a word or a phrase, right, or etc. Or it can be an idea that a person wants to express by using different words, signs, and so on and so forth, right? So effective representation of words meaning, right, has been one of the major challenges, right, because we use a word in different contexts, right? I mentioned about the word bank, right? For example, apple, mouse, these words are used in different contexts with different meanings and so on and so forth. So it is very tough to come up with a single representation or single meaning of a word, right? If you think that, okay, let me curate a dictionary where for every word I have a single meaning, and whenever I need the meaning of that word, I just retrieve that meaning from the dictionary and then I basically solve the problem, right? But this is not going to work because of the complicacy. Okay, so far, if you look at the old school NLP techniques, the way people used to solve the semantics problem is that they used to look at documents, and from documents there were human annotators who were employed to read thousands of documents, and then they used to create big ontology like a WordNet, right, where nodes are, entities are nodes and entities are linked through different relations, right? One sense of an entity is linked to another sense of an entity, and these relationships can be of different types, right? Holonym, meronym, synonym, antonym, hypernym, hyponym, and so on and so forth, right? And then whenever you are interested in understanding a meaning of a word, you look at the ontology, you retrieve let's say the neighboring words of that given word, right, and you try to guess the meaning of it, right? But then people realize that this might not be a good approach. I'll tell you why. And then what is needed is that we essentially need some sort of vectorized representation of a word, right? Computer doesn't know characters, right? Computer knows numbers, right? So we all know ASCII values, right? So you can say, okay, why do we need a complicated vector representation? Let me take a word and let me take the character, let me take the ASCII value of every character, right? And then we concatenate, right? But the problem is that words have different lengths, right? So if you just concatenate all the ASCII values, then the length of the vector would be different for different words. And there are also other problems, right? I'll tell you the other problems. So the simple way to represent a word using a vector is something called one-hot encoding, right? One-hot vector, right? What is a one-hot vector? Very simple idea. Let's say you already have a dictionary where all the unique words are listed, right? And each word has an ID, right? Let's say the word A has an ID, word N has an ID, ... word zebra has an ID, word zoo has an ID, and so on and so forth. ID 1, ID 2, ID 3, and so on and so forth, right? And let's say the size of the dictionary is 1 million, right? So what we do in one-hot encoding, one-hot vector, is that for every word I create a vector of size 1 million, right? And let's say if the ID of that word is 5, right? What I do, I will add 1 at the 5th position of the vector, and the remaining positions will be marked as 0, right? So one position corresponding to the ID will be marked as 1, and the remaining position will be 0, right? Very simple idea. And it also makes sure that words have different words have different representations, right? All the representations are unique, right? But the problems are, there are many problems. There are multiple problems here. The first problem is that now all these vectors are orthogonal, right? So if we take the dot product between two vectors, you'll always get 0, right? Now if you think of if you take a two synonymous words like say motel and hotel, they are kind of same, right? If you take the dot product of these two vectors, you see the dot product would be 0. It means that they are basically orthogonal to each other, although their semantics is almost the same. Okay, so one-hot encoding is not a good approach. The second problem here is that as the dictionary size increases, the vector size will also increase, right? In fact, you may need to recompute the vector again and again, and there are multiple problems. Okay, so if two words share mutually similar semantics, right, this kind of one-hot encoding may not be a good solution for that. Okay, so what is the next solution? The next solution is to look at the WordNet, right? As I mentioned earlier, WordNet is a semi-automatically generated ontology, right, where you see many nouns, verbs, mostly nouns, verbs, adjectives, and adverbs. They are linked through different relations, right? Every word in the WordNet is represented by something called a scene set. Every word has a scene set. Okay, what is scene set? Scene set is a synonymous set or synonym set. Okay, so each word, each sense of a word, not every word. So remember, every word has multiple senses, right? a word can have multiple senses. So every sense of a word is represented by a synonym set or syn set, right? And the description of the syn set is called the gloss. Okay. For example, let's look at the word chump. Okay. The gloss or the description of this word is a person who is gullible and easy to take advantage of. So this is the description of the sense, one sense of the word chump. Okay. And this description is written manually, by the way. Okay, it's a huge manual effort. And what are the different senses of the word chump? Now, if you look at WordNet will say that chump has these many senses. Okay, one sense of chump is same as the second sense of fool. Now remember, fool is also an entry in the WordNet. Fool also has, the word fool also has multiple senses. Sense 1, sense 2, sense 3, sense 4, and every sense has a gloss, right? So the particular sense of the word chump is linked to the second sense of the word fool, right? To the first sense of the word gull, to the ninth sense of the word mark, right? And so on and so forth. Now imagine the amount of effort. Okay, every word has multiple senses, right? These senses are linked, not the words, the senses are linked. Okay, so now this is one entry in the WordNet, right? The word bass, B-A-S-S. If you look at the WordNet ontology, you see that the word bass has multiple senses. The first sense is bass is a musical, some sort of a musical range, right? Bass can also be a fish, right? Bass can also be some sort of singing, male singing voice, bass guitar, right? So it has multiple senses, right? Of course, the pronunciations are different, but the surface word is the same. Okay, so this is the first sense of bass, there's a second sense of bass, third sense of bass, and so on and so forth. Okay, so and if you look at every sense, there's this gloss. These are different glosses. So now one can say that, you know, we don't need one-hot encoding. I will just look at the WordNet, fetch the corresponding sense, and that will be sufficient, right? So what are the problems with this kind of thesaurus-based approach? Thesaurus means resource, right? Thesaurus-based approach or ontology-based approach. Okay. The first problem is that there may be other meanings which are not captured into the WordNet version, right? WordNet has multiple versions, by the way, right? For example, the word proficient and the word good, right? They are synonymous in certain context, but they are not synonymous in all the contexts, right? Secondly, it's very difficult to add newly coined words, right? You need manual effort. For example, ninja, right? Nifty, and so on and so forth. These kind of newly coined words, if you want to add them into the ontology, you need to actually study a lot about their usage, right? What are the senses, where they are used, and so on and so forth, right? And then you also have to remember what are the other senses that can be linked to this sense of nifty, for example, right? So it's actually very complicated. Up-to-date information is difficult to obtain. The other problem is that WordNet mostly considers noun, adjective, adverb, and what else? Noun, adjective, adverb, and verb, right? The other part of speech words are not covered appropriately. This is also subjective, because if you ask one annotator, they may feel that okay, this is not the sense. If you ask another annotator, they may feel that no, this is the sense, and so on and so forth. It depends on who is annotating, right? It requires a lot of human labor. To address this, we will use the notion of distributional semantics. If you remember the second lecture where we talked about NLP, right? I mentioned 3 ways to understand semantics of a word. What are those 3 ways? Ontological semantics, then decompositional semantics, distributional semantics, right? Very good. So distributional semantics is the premise based on which most of the existing word representation techniques are proposed. Okay, and what is the philosophy behind the distributional semantics? J.R. Forth in 1957, he said this famous quote that you shall keep a word by the company, you shall know the word by the company it keeps. Okay, so now based on this philosophy, again, if you go back to old school NLP, right, people came up with many approaches, right? One simple approach is to look at the documents, right? You read the sentence in the document, and you look at the neighboring words of every word, and from the neighboring word, from the neighborhood, you try to imply or you try to guess the meaning of that word, right? For example, the word banking. If you look at this 3 sentences here, the first sentence, government debt problems turning into banking crisis as happened in 2009, right? Here essentially you're talking some sort of crisis, right? Where the next one saying that Europe needs unified banking regulation. Here you're talking about some sort of regulation, rules and regulations. Third one, India has just given its banking system a shot in the arm. So this is more of a banking system, right? The literal meaning of banking system. So you look at the neighbors, and from the neighbors you guess the meaning of that particular word, right? Now how do we systematically do it? We systematically do it using a count-based approach. A very simple count-based approach, where the idea is that, let's say you have multiple documents, okay? You have a bunch of documents, you have corpora, and you see how many times this a particular word appears in a document, how many times this word appears in other documents, and so on and so forth. It's just a count, right? A bag of word kind of approach. Okay, let's look at this example. This is a simple example where right, we basically create this kind of matrix. This matrix is called turn context matrix. What is a turn context matrix? Here rows are individual terms, individual words, individual tokens, and columns are also individual tokens, right? And you see how many times, let's say here, let's say this entry says how many times the word computer appears as a neighbor of the word apricot. Okay, some sort of bigram count table, very similar to bigram count table, but what is the difference here? In case of bigram, these 2 words should appear side by side, wi minus 1 wi, right? But here, when I look at the context, I first decide the size of the context. Okay, let's say I have a context size of 10. I look at 10 words at a time, right? And I'll see how many times the word apricot and computer appear together, right, in the same context, right? And that's going to be the count here. So turn, context, and this is a square matrix, right? So from the turn context matrix, now if you look at every row, okay, now you can think of every row as a vector, right? Let's say first row is a vector for the word apricot, right? When apricot is used as a term, as a term, right? You can also and apricot will also appear in a row, right? Here also you will see an entry for apricot, right? And there will be a column corresponding to the word apricot, right? So that column can be treated as a context vector for the word apricot. So row can be treated as a turn vector for the word apricot. Column can be treated as the context vector for the word apricot, right? Now it is up to you to decide which vector you want to consider. One option is that you take both the vectors and you sum them, right? Other option is that you try with context vector as well as turn vector and see which one is useful, right? Very simple idea. So let's say you are given this kind of documents. It's a stylized example. There are multiple sentences, right? You scan through the documents and you create this kind of matrix. Okay. So now if you look at two entries here, let's say apricot and pineapple, you see both these words co-appear with similar context words pinch and sugar, right? But they did not co-appear with the context words artwork or computer data, right? So you can say that, okay, maybe these two words are similar. Okay. Similarly, if you look at digital and information, you see both these words co-appear with the word computer and data, right? Also results, but they did not co-appear with the word artwork, pinch and sugar. So maybe these two words are similar, right? A simple idea. You look at you take every column, you take a pair of columns, you do some sort of dot product, cosine similarity, and then you figure out the similarity, right? So here, what are the problems? The first problem is that again this matrix size can increase with the increasing number of vocabulary terms, right? Second problem is that vector size will also be very large. If the vocabulary has, let's say, millions of words, then the size of the vector should be very, very large. And also this matrix is sparse. Most of the entries are 0, right? A sparse matrix. The fourth problem is that we see stop words, right? Frequently appearing words, particle, preposition, right? Their corresponding entries will be very, very high, obviously, right? So we need some sort of normalization after this, right? So what we do here, so from term a raw count of terms and context, now we move towards an advanced, slightly advanced concept called TF-IDF. Okay. So what is TF-IDF? In TF-IDF also we are going to create this matrix. Remember this. Okay. TF stands for term frequency and IDF stands for inverse document frequency. TF-IDF. Okay. Let's first discuss TF. So what is TF? Term frequency of a term T, right, with respect to a document D is the number of times that particular term appears in the document. So remember, this is a tuple. This is a function of T comma D. You can't say that the term frequency of T is this. You have to say the term frequency of T with respect to the document D is this. Okay. So by the way, when I say a document can be a Wikipedia document, a document can be a novel, a document can also be a paragraph, a document can also be a sentence. It depends on how you define a document, right? Because if you have only one document, then how do you compute TF-IDF? You consider every paragraph as a document and then you measure this. So count of this, a raw count of this. Now the raw count will be very, very high for, again, frequently appearing words, stop words, right? To just dampen the effect of this, we squash this a bit. Instead of taking the raw count, I take the log of the raw count, right? Log of the raw count, and if the count is 0, then log 0 will be undefined, right? Then therefore we just add 1. That's a smoothing technique. So log count plus 1 is the TF measure. What is the problem in TF? The problem with TF is that, again, frequently appearing words, stop words, will have very high TF count. Okay. To address this, we will use another component of TF-IDF called inverse document frequency, IDF. Okay. IDF. So what is inverse document frequency? Let's first see what is document frequency. A document frequency is the number of documents where the particular word appears. It is not the number of counts of all the documents where this particular entry appears, right? Only the number of documents where the particular entry appears. It's called document frequency. Okay. Let's say there are two words, Romeo and action. The word Romeo appears only one document, not in the other documents of Shakespeare, for example. Okay. So the term frequency will be very high for that document, but the document frequency will be very low. Why? Out of, let's say, 1,000 documents, only one document has this word Romeo, right? So document frequency will be, let's say, 1. By the way, what is this collection frequency? Collection frequency is the count of the sum of count of this word across all the documents. Term frequency is with respect to one document. Collection frequency is the sum of counts of all the counts in all the documents, and document frequency is the number of documents where this particular entry appears. Clear? Okay. So the word Romeo will have a document count of 1, whereas the word action, which is a more generic word than Romeo, right? Let's say is collection frequency still 113, right? But this collection frequency is distributed across documents. It is not that only in one document the word action appears 113 times. In total, it appears 113 times, fragmented, right? And let's say there are 31 documents where the word action appears. Okay, so this is document frequency. Okay, now I will take the inverse of this, inverse document frequency. So 1 by 1, 1 by 31. Now, what is the meaning of this inverse document frequency? When we take the inverse of this, if a word appears in all the documents, like the word action or stop words, if it appears all the documents, its importance will be reduced. Which is obvious. We don't want to capture those words which are which appear in all the documents. Rather than this, we should consider those words which are representative, right? So this is IDF. This is the formula of IDF. So DF, 1 by DF is inverse document frequency, right, of the term T. Remember, here IDF is a function of only the term T, not T comma D, right? And we take a log of this, and just to normalize the value, we normalize it by n. What is n? N is the number of documents. Okay, so we just normalize it by n. Now this is the generic IDF formula, but as you can see, DF, if DF is 0, then what would happen, right? So sometimes we also add 1 here, right, to the denominator. Sometimes what we do, we also add 1 here. There are multiple variations of TF IDF, right? In TF also, term frequency, instead of taking the log of count, right, what we do, we normalize it by number of tokens in the document, right? Let's say the number of tokens is V, for example, right? Sometimes we normalize it by max count, not the total count, max count, and there are different variations of this. Okay, now look at the IDF value of the different words. The word Romeo has the IDF value of 1.57, whereas the word good or the word sweet, which are frequently occurring in all the documents, their IDF values are 0. So you are penalizing those words which appears in all the documents. Okay, so the combined version of this metric is TF IDF, where we multiply TF with IDF. Right, so this is the formula of TF IDF. This is the raw count table, right, before TF IDF. This is the TF IDF table. Okay, in the raw term document matrix, you see that there are entries like let's say the word battle, right, appears only in the Julius Caesar novel, right? Its count is 7, but in TF IDF its value is significantly high, 0.22, right? Whereas the word fool, which is kind of a common word, whose count is pretty high, 58, but TF-IDF is pretty low. So from raw count we moved to TF-IDF, right? So every entry here that is the TF-IDF value for that document, right, with respect for that word with respect to the document, right? And each row is a vector now, similar to earlier case, right? So it addressed the problem of frequently appearing words, right? But there are still other problems. For example, if the document size increases, the vocabulary size increases, the matrix will increase, right? The vector size will also increase. There are so many zeros and so on, sparsity and so on and so forth. Okay, so now these are the problems of count-based approaches. So one can say that so this sparsity problem or bigger size matrix problems, right, we can easily address by doing some sort of decomposition, right? We can use SVD, for example, right? On top of this count matrix or TF-IDF matrix, I do SVD and then I decompose it, right? And we'll take the decomposed version of it. But SVD is again time consuming, right? It is quadratic in the number of rows and columns, and the other problem is that as new words comes in, right, you have to reconstruct the table, you have to again apply SVD on top of this and so on and so forth. The last and most important drawback of this kind of count based matrix is that it doesn't consider the ordering of words, right? I look at a particular context, and within the context, this context window of size 10, for example, all the words are same, right? It's a bag of word representation. All the words are the same, right? So it doesn't take into account the fact that if some word appears before the other word or some word appears after the other word, their meaning may change. Okay, so SVD may not be a good approach because of the quadratic complexity and incorporating difficulties in incorporating new words and so on and so forth. Okay, so to address this problem, now we move to the recent approach called Word2Vec, a prediction based approach. We have seen count based approach. Now we look at prediction based approach. Okay, so let us go back to 2013 when Google, Thomas Mikolov and Jeff Dean, they came up with the idea of word vector, and this term word vector was coined that at that time. Word vector is nothing but the vector that we have been discussing, but it is dense now. It is not of size 1 million. The size could be 100 or 200 or 500, right? So word vector is a dense vector. Now why a dense vector is important instead of a sparse vector? Because if the feature size is, if the feature number of features is high, right, it may be prone to overfitting. We need lots of parameters to train, right? We all know scarce of dimensionality, right? So if we squeeze it, maybe we don't need to of course we don't need to train many parameters. The second problem is that it will be more generalizable, right? The other good part is that if you take this kind of dense vectors, right, oftentimes we see that the words car and automobile, right, they are synonymous. But if we look at the traditional count based approaches or one not encoding kind of approaches, this kind of synonymous words are not captured properly. In fact, oftentimes we say that if a word W co-appears with the word car as well as with the word automobile, right? Let's say there's a word W1 which co-appears with the word car. There's a W2 which co-appears with the word automobile. W1 and W2 can also be synonymous, right? So this kind of inference may not be very straightforward from a raw count based approach. Okay, so Word2Vec was proposed in 2013, and in the Word2Vec package, there are two types of approaches, right? Which are almost the same, but prediction wise they are slightly different. Remember, these are prediction based approaches. We are moving from count based approach to the prediction based approach. Okay, so the first one is called CBOW, continuous bag of word model, and the second one is called the skipgram model. Okay, so the idea is almost the same. In, let's say there is a word, there's a sequence of tokens. Let's say I am going to school, right? I want to measure the vector corresponding to the word going. I want to measure the word vector corresponding to the word going, right? In CBOW, what I do, I will take the context tokens, right, to predict the word embedding of the given word. In skipgram, I will use the center token to predict the word embedding of the context words. It's just the opposite. I have a sequence of words, sequence of tokens, and let's say there is a central word. For example, in this case, the central word is going, for which I want to predict the embedding. In CBOW, I will look at the context words to predict the representation of the central word. In skipgram, I look at the central word to predict the representations of the context words. Right? In a neural network terminology, this is very straightforward. Let's say you have a multi-layer perceptron kind of network, a two-layer network, right? In CBOW, what I do, I feed the representation of the context word, and I will try to generate the representation of the central word. In skipgram, I feed the representation of the central word and try to generate the representation of the context word. Okay, so let's focus on skipgram because this is more popular, right? Skipgram with negative sampling. Okay, skipgram with negative sampling. We'll discuss what is negative sampling and so on. Okay, so Word2Vec is an unsupervised approach. I would say this is a self-supervised approach. You do not need any labeling, any human labeled data, right? Number one. Number two, this is just a prediction task, right? A simple logistic regression task. It's a simple logistic regression task. All of you know logistic regression? It's a simple logistic regression classifier. It's a classifier which will classify that this word is not a context word, this word is a context word. That's all. Very simple idea. Okay, so let's look at the approach. So we have a target word T. Now remember, we will use two terminologies. One is called the target word, and the other is called the context word, right? T and C. Okay, given a particular target word, I will look at what are the context words. And how do we identify a context word? I have this window, right? I have this window of size 10. I have the documents, multiple sentences. I move the window one step at a time, right? At every step, I look at 10 words at a time, right? Let's say the middle word is a central word, and the remaining 9 words are the context words, right? So what I do, for every central word, I make a pair, right? Let's say WT is a context is a target word, and WT minus 1, WT minus 2, WT minus 3, right? WT plus 1, WT plus 2, WT plus 3. This is the context size, moving window size, right? And there are of course other words here. It's a WT plus T minus 4, WT minus 5, right? WT plus 4, WT plus 5, and so on and so forth. And this is my sliding window. Okay, this is my target word. So what are the positive context words? The positive context words are WT. So for WT target word, the positive context words are WT minus 3, right? WT minus 2, WT minus 1, WT plus 1, WT plus 2, WT plus 3. These are the positive context words because these words appear, these words co-appear with the word WT within the context. So, right? So these are the pairs. These are the positive pairs. Given a particular window size, right? I will first identify the context words and make these pairs. What are the non-context words with respect to this context size at this position? What are the non-context words? Non-context words are those words which are outside of this particular window, right? So there are if the size of the document is n, there are n minus how many? 3 plus 3, 6 plus 7, n minus 7 tokens which are non-context words, right? Okay, so I will sample non-context words from the document. So this is my context word pairs. I will sample equal number of non-context pairs from the document. In fact, in Word2Vec, what we do in skipgram specifically, we take k times more negative samples. These are negative samples. These are positive samples, and those are negative samples. Non-context words are negative samples. So if I take 10 positive samples, I will take 40 negative samples 4 times or 5 times. Why? It will give you more evidence, right? Not only that, sometimes what happens is that when you sample negative examples, it may happen that some of the positive examples can also come, right? Because you are sampling from some distribution. It may happen that some of the positive samples can also come. In fact, that particular word can also come as a context, negative context, right? Of course, you can have tricks to remove those duplicates, but it is always safe to consider more negative examples. We will discuss how to sample negative examples later. Okay, so this is the sequence of tokens. I fix the context window. I sample positive instances, negative instances. I curate positive instances, sample negative instances. Then I run this classifier. Okay, and the classifier will classify positive instances from the negative instances. Now, how I will tell you, right? So again you move this context window one word forward, right? Again you curate all these things. Again you run the classifier, and you keep on doing this thing until unless the entire document gets scanned. This is the overall philosophy. Okay, let's look at examples. So let's say this is an real example: lemon, a tablespoon of apricot, jam, a pinch. This is a sequence of words, right? And let's say the context window is this one from here to here. Okay, and the target is apricot, tablespoon and of are context words, jam and a are also context words, and other are non-context words, right? These are context pairs. So for every word W, now this is W, okay? For every word W, we have a context vector C. Now remember, this W, this word W is represented by a vector, the word embedding vector, which we are going to learn, right? Through this classification, we are going to learn the embeddings of W and C. What is C? C is the context words, and W is the target word T. We need a representation for C, we need a representation for W, right? And over the iterations, we will learn the representations of W and C. We start with a random initialization of W and C. It can be, let's say, one-hot encoding, for example, simple, or it can be random initialization, and then you keep on iterating, right? Okay, what is the task of the classifier? The task of the classifier is that given a pair of instances W and C. What is W? What is W? W is the target word, central word. What is C? C is the context word. Given this pair W and C, we measure the probability that this is a positive pair. So given that we have W and C, what is the probability that this is a positive instance? This is a positive instance. If it's a context, it's a positive instance, right? If C is a negative instance, then I will measure, given this probability, given this tuple W and C, what is the probability that this is a negative instance? So we will measure these two probabilities. Okay. Now negative probability is same as 1 minus positive probability, right? So essentially we will measure this positive probability. Okay. What is the probability that a particular pair is a positive pair? Okay, so how do we measure this probability? We measure this probability using dot product, right? Dot product is a measure of similarity. We all know what is dot product, right? Now let's look at the equation here. It's a very simple equation. So I mentioned that this is just a classifier. This is a logistic regression, right? To measure this probability that W and C are positive instances, right? W and C pair is a positive instance. What I do, I measure this probability using a sigmoid function, right? What is the sigmoid function, right? And the beauty of the sigmoid function is that it basically squashes everything between 0 to 1, right? Machine learning researchers always prefer this sigmoid function because not only it produces a probability, but also the derivative has some beautiful formula, right? If you take the derivative of sigmoid, this is essentially sigmoid into 1 minus sigmoid. And there are also other properties, very interesting properties. Of course, if you ask a statistician, they will say that, you know, I will not consider sigmoid as a probability, because probability has certain axioms and certain other properties. But for a machine learning researcher, I think this is a good enough function, right? So sigmoid of C and W, remember C is a vector, embedding vector, right? W is also a vector, right? So this is computed by 1 by 1 plus e to the power minus C times X. This is a dot product, okay? Right? And how do you compute the negative one? 1 minus positive. Remember, what is 1 minus sigmoid of X? 1 minus sigmoid of X is sigmoid of minus X. So sigmoid function has very beautiful properties, right? So 1 minus the sigmoid is basically sigmoid of minus of that, right? And if you do this math, you see that this is essentially this one, 1 by 1 plus exponential of C times W. Okay, so now this is for one pair. This is for a single pair of word and context, right? Target and context. There are multiple such pairs, right? If the context size is 10, there are 9 such pairs of positive instances, and there are 40 such pairs of negative instances if it is 4 times, right? So this is for one pair. So how do we then consider all the other pairs? For other pairs also I measure this, and we assume that all these pairs are independent, right? If they are independent, then this is just a product of all the probabilities. This is just a product of all the probabilities, isn't it? There are L such instances, right? And sigmoid of Ci times W, where I ranges from 1 to L. L is the context size, the window size. Is this clear? Okay, so this is essentially all the probabilities considered together. So we do not consider the sum, we do not consider the product. Oftentimes we take the log of it, right? We take the log of this probability, and which will essentially be the sum of all the logs, right? Right. So what we have done so far? Tell me. We fixed the context window size, right? For every context window, we sample positive instances, and negative instances. We curate positive instances and sample negative instances, right? And then we measure the probability, okay? And then the positive probability should be higher than the negative probability. That the classifier needs to make sure, right? The classifier basically, logistic regression works based on the log likelihood estimate, right? So we will have this log likelihood estimate, and that's my objective function. Then we take the derivative, because this is the objective function. We maximize the log likelihood, right? Then we take the derivative. What are the parameters here? The parameters are the vectors, the C and W vectors. Now here's the question. So tell me, for every word, how many vectors we are computing? 2 vectors, right? C and W, or C and T, right? Where a time when the word acts as a central word, and the time when the word acts as a context word, right? So if you think of this matrix, if you think of the embedding as a bulky matrix, and assume that there are v number of vocabulary tokens or vocabulary entries present in the document, right? V is the number of tokens, right? So we have V entries here, and we have V entries here, right? Let's say from A to zoo, here from A to zoo, right? And these entries, the upper part of the matrix represents the target embedding, and the lower part represents the context embedding. So we are essentially learning 2V number of vectors, right? And what is the size of the vector? Is the hyperparameter. You have to decide beforehand. Let's say the size of the vector is 10, right? So what's the size of this matrix? 2V times 10. This many number of parameters we are updating. Okay, so now look at this one. So this is this bulky matrix which we are estimating. So the word starts from aardvark to, let's say, zebra, right? And this mod V size part of the matrix corresponds to the target words, and the similar mod V type size submatrix corresponds to the context words. Okay, and when I say that the word aardvark, for example, the word aardvark and the word apricot, just again for the sake of give an example. Let's say when I say that the target word is aardvark and the context word is apricot, let's say, and the apricot is a positive context for the word aardvark, right? Let's say this is my initial matrix when you initialized it, right? And when I say that this is a positive context of this, what does it mean? It means that over the iterations, I will try to move the representation of the context of apricot closer towards the target of aardvark. Let me repeat what I just mentioned. Aardvark is the target word and apricot is the context word, right? When you initialize this matrix at the beginning, all this initialization happened randomly, right? And over the iterations, what is the target? The target is that positive context should come closer to the target and negative context should basically be far from the target, right? So over the iterations, I will update this matrix such that the positive context will come closer and negative context will basically go far. So apricot, you will see that over the iterations, right? If you look at the embedding space, let's say these dots indicate different embeddings, right? In the vector space. Let's say this is aardvark and this is apricot. This is the target of aardvark. This is the context of apricot, right? Over the iterations, you will say that this will move closer and closer. These two things move closer and closer. and the negative instances will move further and further. Okay, now let's look at the training process of Word2Vec. Okay, at every context window I have a target and I have a context. I have multiple contexts, right? So in this case, apricot and tablespoon, apricot and off, apricot jam, apricot A, these are positive instances, right? And we sample k negative instances from the remaining documents, right? For example, apricot artwork, apricot my, apricot where, apricot if, these are all negative instances. Okay, so and then I train the logistic regression so that this and this, the positive pair should be classified from the negative pair. Okay, how do we sample negative examples? We sample negative examples based on the unigram distribution, right? So for every word I have a probability from the document. I can easily measure the unigram distribution of every word, unigram probability of every word, right? So there is this unigram probability, and then I sample every time I toss a coin and sample a negative example from the unigram probability. Okay, but with a small tricks here, because what will happen if I only consider unigram probability? What will happen? Only the words which are frequently occurring, because their probability is high, those words will be sampled again and again. But those words are not at all meaningful, non-contextual words, right? If I keep on sampling word if I keep on sampling the word, let's say the or a, right? These are not meaningful words, right? So what I do, instead of a raw unigram probability, I will use some sort of modified unigram probability. So count of this W by sum of count, this is the unigram probability. I will essentially use another parameter alpha. So count to the power alpha by sum of count, and every count has this alpha, okay, as a power. Why this is needed? This alpha, addition of this alpha will give you a slightly higher edge to the rarely occurring words or low frequent words, right? Let's if you are not convinced, let me give an example. Let's say there are two words A and B, and these are the raw unigram probability 0.99 and 0.01, right? Now if you use alpha, if you add alpha as a power, and let's say the value of alpha is 0.75, okay, so the modified unigram probability of A is 0.97 and the modified unigram probability of B is 0.03. So 0.03 is higher than 0.01, although in a highly frequent word has still higher frequency, higher probability, but at least after this modification, rarely occurring words, they will have slightly higher probability, and high frequent words will have slightly lower probability, right? And now you can control the value of alpha. So this is the probability based on which I will sample negative instances. Okay, so how to learn word vectors? We will maximize the target word context word pairs probability. We will minimize the target word negative context word pair probability. This is the target. So what is the final objective function for the logistic regression? Logistic regression maximizes the likelihood, right? Or minimizes the negative log likelihood, right? So probability of the positive instance, and there are k negative instances I have sampled, right? Negative probability of positive instance and the negative instance, and we will see that whether this this pair, this negative pair, is what is the probability that this pair is a negative pair. So P of W C pos. What is C pos? C pos is the embedding of the positive context, right? And W is the target word, right? So what is the probability that this is positive, right? Similarly, I have a W and C neg. Okay, this is a negative, this one negative context, right? What is the probability that this is a negative context, right? Okay, and there are k number of such negative samples that I have already sampled. So I take a product of all this k and I maximize both this and this. I mean, you can say that why I am maximizing this? I should minimize this. The second part, what is the second part? What is the second part? Given a target word and a negative context word, what is the probability that this is a negative instance, right? Should I maximize or should I minimize? Maximize, right? I want to maximize this also. I also want to maximize this. So I take the product, right? Log of this. So this is the log likelihood minus negative log likelihood. I want to minimize this. Okay. Now, if you do some small arithmetic, so you move log inside. So log this plus sum of log this, right? And we have already seen that. Okay. So what is this, by the way? P of minus given W comma C neg is same as 1 minus P of plus given this, yes, right? This is same as this. And how do we measure this probability? Using sigmoid and dot product, right? So this probability is replaced by sigmoid. This will be replaced by sigmoid. 1 minus sigmoid is 1 minus sigmoid x is sigmoid of minus x. So this is same as sigmoid of minus x. Okay, so this is the objective function that I want to minimize now. Okay, and what are the parameters? Parameters are C positive, C negative, W. By the way, C positive, C negative, these are just notations, right? Both of them are C, right? Just for our understanding, C positives are those instances which are positive, and C negative are those instances which are negative. So in this bulky embedding matrix, we have only W and C, or whatever T and C. Okay, this I already mentioned, and I will use gradient descent to update this. So this is the loss function. Okay, there are parameters W, C neg, and C pos, and we take the derivative. Let's look at the derivative. A very simple, straightforward derivative. You take the derivative of this with respect to C pos. Okay, so this part will be ignored, right? We will only look at this part, log of x, 1 by x, right? So this will be 1 by sigmoid, right? And then we take the derivative of this, right? What is the derivative of sigmoid? Sigmoid into 1 minus sigmoid. So sigmoid into 1 minus sigmoid is sigmoid will cancel out, right? 1 minus sigmoid will basically remain. Now we already have a negative here. So this will be sigmoid minus 1. And of course, there's a W. So this is the derivative. Similarly, if you do a small calculation here, this will be the derivative with respect to C neg, and this will be the derivative with respect to W. Okay, once we obtain the derivative, these are the update rules. The positive vectors will be updated using this formula. The negative vectors will be updated using this formula, and W will be updated using this formula. Right? Now we obtain two matrices, W and C. I mentioned multiple times, two matrices, W and C. Now you can ask which one I should choose, right? The best option is that you choose two things separately and see which one is better. The default option is that you take the sum of apricot using apricot acting as a context apricot acting as a target, you take the sum of both the vectors, and that's going to be your final vector. Word2Vec is a static embedding. Remember this, it's a static embedding, meaning that for every word W, you will only obtain one vector. I mean, of course, you can say two vectors, but ultimately one vector. It is not the case that for every senses of this word, you will have different vectors. Modern approaches like BORD kind of methods, there you will see that you will get contextual embeddings. Okay. Okay. So summary. This is the summary slide. We start with a random initialization of this entire matrix. What's the size of the matrix? D dimension V plus V. So 2V times D matrix. We start with the random initialization, and then I move the sliding window. Every movement I will curate positive instances, negative instances, k times more negative instances. I will run the logistic regression, update the parameters. I again move, run, and so on and so forth. Okay, so this is prediction based approach. What is the difference between count based approach and a prediction based approach? Count based approaches including TF-IDF, raw count, and prediction based approaches like Word2Vec, right? What are the differences? Count based approaches create this matrix one time. Scans, you just scan all the entire document and create the matrix, and you are done, right? So it preserves the statistics very, very, very carefully. Whereas in case of Word2Vec, there is no such thing, right? Count based approaches, the negative part is that as the size increases, the matrix size will increase, and you need to recompute all the entries. Here, as the size increases, you may just need to learn, or you may need to run the logistic regression one more time. Okay. So, couple of small tricks that this Word2Vec paper considered. Another tricks that they considered is called subsampling frequent words. Let's say this is the sentence: the quick brown fox jumps over the lazy dog. Okay, and this is my window. What are the samples I can curate? The, quick, the, brown, right? From here, let's say quick, the, quick, brown, quick, fox, and so on and so forth, right? If you look at here very carefully, quick, the, quick, and quick, the, they are basically the same, isn't it? Because ultimately we will take the dot product of two vectors. So I can ignore one of these instances. The second problem is that the word the, right? The second problem is that the word the is not at all a very meaningful word, right? Because it is unclear whether the word the acts as an article, acts as a meaningful article here, or the literal meaning of the is useful in this context or not, right? So what we do here in subsampling is that we use another probability, and with this probability I will remove some of the words from the documents, and I will not consider those words while curating the positive samples and negative samples. What does it mean? Now this is the probability. This is again kind of an unigram probability, but small changes here and there, right? So P of W is a probability of a particular word. This is, what is Z of W? Z of W is the raw frequency, okay, of the word WI. And this is some sort of complicated formula that they proposed without much rationale behind it, right? But you can also think of many such formula which can guarantee that this trend remains as it is. What is this trend? It says, so the x-axis is ZWI and y-axis is PWI. Okay, so if a word is less likely in terms of frequency, they will be sampled more. and if it is highly likely, they will be sampled less. Zipf's law, meaning that if a word appears a lot of times like the word the, you will ignore or you will remove that word from the document. If it appears less number of times, you will keep those words. When I say remove a word from the document, means with certain probability, not all the times, okay, with certain probability. So let's look at some of the values, right? So in order to make the value of p to be 1, if you really want to make a probability to be 1, right, the frequency, the frequency should be 0.26%, less than 0.26%. So it means that if a word appears in a document 0.26% of time, it is highly likely with probability 1 you will sample that word. Okay, if the word appears, right, with this probability, right, you will with 50% chance you will with 50% chance you will sample that word. If a word appears 100%, what does it mean? It means that there is only one word in the document, right? I mean, there is only one word appearing multiple times in the document. There is no other word. So the chance that this word will be sampled is 0.033 probability. This is just a hack to remove frequently appearing words from the training instances. That's all about Word2Vec, right? This is a very nice analogy that they showed in the paper, that with now you have all these embeddings, right? So with these embeddings, now you can do all sorts of word analogy test, right? In fact, you can do linear operations here. There's a beautiful example. You take the embedding of king and you subtract the embedding of man from the embedding of king. So king, the word king has an embedding, the word man also has an embedding. Okay, you subtract this from king, you get a resultant embedding, right? So, and then you add the embedding of woman, right, to that resultant embedding. This will be equivalent to the embedding of queen, right? So you subtract man from king, add woman, you get the embedding of queen. What are the problems of word embedding? The first problem is this is a static approach, right? It doesn't consider different senses of it. The second problem is that when an unknown word comes in the test set, word embedding is already trained on a training set, right? You have a dictionary where the embeddings are already stored. Now in a test set, when you see a new embedding, when you see a new word which did not appear in the training set, how do you get the embedding of this? You will not get it, right? To address this problem, what people suggested is something called subword embedding. So from word, I move to subword. What is a subword? Subword is a sequence of characters, right? So the method that was proposed by Facebook is called fast text. Fast text is a subword embedding method, right? What is a subword embedding method? Very same as skipgram, right? So here, and again, I will not go into details of this. So the idea is that in skipgram word embedding method, in Word2Vec, what is our vocabulary? Our vocabulary is the set of words, right? Here, the vocabulary is set of subwords. And how do we define a subword? A subword is defined by n-grams, right? Let's say the word where, W-H-E-R-E. Here, if the n-gram size is 3, I will take W-H-E, H-E-R, E-R-E. These are 3 subwords, right? Along with this, I will use this angle bracket as the start of the word and the end of the word, and those angle brackets are also considered as characters. So you have this as a n-gram, as a 3 gram. This is also 3 gram character, 3 gram character, 3 gram character, 3 gram character, and the word itself. So for every word, I have a set of subwords, that word itself, and the other n-gram characters. Once we got it, I will just run the skipgram. I will just run the skipgram, and skipgram will give you subword level embeddings. Now let's say a new words come in, a new word comes in, which is let's say nifty. Okay, so the hope is that in if for this subword I have an embedding, right? This n-gram character, this character n-gram has appeared maybe, right? So I will take the subword embedding of NIF, I will take the subword embedding of IFT, I will take the subword embedding of FTY, right? And of course this angle brackets, right? And I will sum them up. Okay, so this is the idea of first text. I'll stop here, and maybe in the next lecture I will start discussing glove embedding. Thank you.